Sharing my screen. There we go. Okay, so I've set up in our Zymposium repository a basic backend server that we're going to be using a little bit to motivate the topic today, which is basically going to be creating an API DSL similar to the one that I presented at ZIO World. So there's a talk on YouTube if you haven't seen that, but no worries if you haven't, because we're going to walk through the motivation a little bit and also build a simpler version, whatever we can get through in the next hour and a little bit. So right now I just have this very basic server that's made with ZIO HTTP, and it's using the sort of the current DSL, which is really just using a clever pattern matching syntax, the same sort of clever pattern matching syntax that you see in other libraries like HTTP4S. And so here, what you do is you define a server by basically calling this collect method, and you create this partial function using just an anonymous case pattern closure thing. And so you match on the method and then the path, basically. So you get the method and the path, and they're separated by this little arrow. And these are all, if you command click into these, they're these little unapply objects that basically do pattern matching for you. I think we should, I'm not sure if we spent, I'm losing track if we did a video on
I don't think we did a video on pattern matching here.
No. So that would be interesting to do at some point, to dive into how those things work, because they're pretty fun and pretty powerful. But for now, it's an implementation detail. But you use this syntax. And it works all right, but there are a couple of drawbacks with it. One is there's a sort of performance drawback, where every time you do a pattern match, if we do click into this unapply method, which is sort of what is called behind the scenes, this powers pattern matching, you'll see a couple of things happening, which is generally that there are tuples and options. So every time you try to nest into a pattern, you're allocating both an option and a tuple, or sometimes a tuple if there are multiple arguments, but at least you're allocating an option. And it also can be a little awkward. They sort of have to be nested in a very particular way, and it can be a little limiting sometimes. For instance, this double bang, this angry rabbit symbol, is another pattern matcher, which I can't seem to find with autocomplete, but whatever. I think it's in here. Request syntax? I don't know where it is. Bang, bang, there it is, yes. So it's just a stable identifier to the end of a path, this thing here. And you kind of have to have that at the beginning of every path. Even though it would be nicer to do this, potentially, this will not actually work correctly. I don't believe. Don't seem to be getting a compiler error, but it's just IntelliJ not knowing. But you do need this bang bang. And there are other limitations as well. It's not quite the ideal API for doing this sort of thing, but it does work, and it's not bad to have out of the box by any means. Let me just add one more route here. So I have a very basic, just to walk through what's happening, I have a very basic ZIO service called users, where it's just a trait where I can create a user. With an email, I can get a user, and then I can get all the users for now. So we're gonna make a get all path, because I don't have that yet. So what I'm gonna do here is I'm gonna say case method get, and this time I'm going to just go to /users without the ID, and I'll say users.all, and it should be clever enough to do the rest for me. So I'm going to delegate to this users method, users.all method, that's being generated by this macro for me, and it's going to get all the users that are currently stored just in an in-memory ref, and then we're gonna have a JSON response by JSONifying that list of users. So if I go to the browser and restart, we should see an empty list because I didn't sort of seed it with any users. But I also have Postman open, so I can create a user right here with the email cool@gmail.com, and I've just done that. Now, if I go back here and refresh, we here have the our user that we created. And I could do another one, kit@gmail.com, and refresh, and now we get some more. So that's great. So a very basic server API here. Nothing too miraculous. There's also a get path that's going to match a particular ID. So if I steal this right here and go to users / that path, now we'll just get this user. So your typical RESTful API. As you'll see here, though, I'm doing some unsafe stuff. Like I'm calling UUID from string, which does throw. So if I were to not have a properly formatted UUID, it's going to just not really respond with anything, I suppose. Oops. Let me refresh this. And if I do something else, okay, we get an internal server error. So that's great. Yeah, invalid UUID string. So luckily they format this for us with this lovely modern default response, but not ideal. So yeah, we probably don't want it to blow up in that case. So we're going to basically work on building an API DSL that essentially allows us to describe these sorts of things as values, sort of the interface to our server. Because a server really is just a strange API, right? Everything in code is, if you squint hard enough, kind of calling functions or methods. And that's what a server is. It's just that it has to be done in this sort of strange HTTP protocol. We don't have the niceness of sort of Scala to have our server API written in this way. But if we could, it would sure be nice to say something like, well, we want to have all users, which would return a ZIO of a list of users, create user to create a user, and then get user, where we would take a user ID, user ID, and get back an option of a user or something like this. And basically, while we can't quite do this, we can create ourselves a declarative API that's going to a little DSL that we can use to create values that represent this sort of interface. And from that, we can generate servers. So that's kind of going to be the goal today. So let's start with some aspirational API for this. So what I'd like it to look like is something like this. And so instead of doing this here, what we want to say is API get users / and then I guess this is a UUID. So I might do something like this, or I might do like param UUID. It doesn't really matter. For now, I'll just do /UUID. And then, so this kind of describes the input, which is users, sort of the method name, if you will, which is the path, and the argument, or one of the arguments, which is a user ID or a UUID. And then the next thing we want to do is describe this result type as well. That's part of the signature, and that's part of what we want to do if we really want to basically encode the idea of an interface as a value. So I'm going to say output is going to be an option of a user. So this is going to be get us back this API value. So this is going to sort of be a get user API. And we want this to be a typed DSL. So it's going to actually have a couple of parameters. The first might be the value of this UUID that we would have parsed. And the second will be the option of user, basically our specified return type. So it's this value that represents the interface of just one of our sort of methods here. So it's this method definition as a type. And so far, like, what does this mean? And we don't know. This is just syntax. This is just syntax, and syntax by itself is actually kind of meaningless. And I'm only able to sort of come up with this vaguely because I have a vague idea of what I wanted to accomplish. So this isn't really showing the full story just yet, or even a process by which you can sort of, if there's anything useful here, that you can use it on your own projects when designing your own DSLs. So let me actually take a step back. And there's this concept that kind of relates to why I was so interested in we did a video recently on free structures and church encodings, which was definitely very highfalutin and conceptual. But the idea that I really wanted to drive home during that was this duality of data and functions, and particularly the idea that data is only as useful or is only good as good insofar as it is interpreted. There's a much further way of saying that, but basically, data is only as good as its interpretation, and so data here is kind of our syntax, and the other fancy word for interpretation is semantics. So syntax is kind of meaningless without interpreting it into its semantics. So when designing DSLs like this, the declarative DSL is very much the syntax. It's your programming language. It is the abstract syntax tree for your DSL. We can use so many 3-letter acronyms. It's the ADT, which describes the AST for your DSL, and that's what the syntax is. But that's meaningless if you don't have semantics. And in fact, it can be hard to sort of come up with semantics in a vacuum. Maybe you've done that before. I've certainly done that before, where it's like I have this vague idea of what I want to do, and I start with the API that I'm describing. And then I realize later on that I have not encoded all of the information I need to get done what I eventually need to get done. Sorry, my brain's a little flaky this morning. We'll see what happens. So it can be good to start with the semantics, or kind of both. I like this idea of the function arrow, this very functional construct of A to B. It tends to be a nice mental guide, an intuition pump, to steal a word from Daniel Dennett. So it can be used as sort of this heuristic to guide you in your designs. Because I often flip back and forth between what am I going for and what do I start with? And you can kind of zoom in. Often this is a multi-step process, so you have these intermediate steps. But at each stage in this process of design, you have sort of a target and you have a source. You have your domain and your range, if you will. And so thinking in this form, maybe this sounds pretty abstract, can be kind of helpful, but I'll kind of hopefully can show that process a little bit. So let's start with our semantics. We took a brief glance at the syntax, just because I wanted to give you an idea of what we're going for with this library. But if we were designing this from scratch, we wouldn't necessarily be able to just pull that out of our butts. So we might want to start with the semantics. So what does it mean to have, what is our goal here anyway? What are we trying to make easier? So one of the goals is to basically generate a server. Is that even possible to generate a server? So our syntax is going to be something we don't know yet, but our goal is kind of to generate a server. And so that, what does it mean to be a server? We kind of have to keep drilling into these words and unearthing them until they become concrete enough that we get an idea of a potential implementation. So a server essentially is this function that goes from request to response, which is kind of what this HTTP type is. It's really a glorified function from A to B, request to response. And that's great. But if we think a little, maybe zoom in on that even more, we'll realize that, well, we don't want to build all of the server functionality with our library. In fact, that's kind of its own concern about parsing this request from, what's really happening is we're getting some binary data and then going back to binary data. So we've already kind of shrunken our domain a little bit by zooming in here. ZIO HTTP takes care of this process for us. It will go from it'll open up the socket, it'll listen for requests coming in, and it'll parse it into some nice request structure that it has, some trait request here. It will also give you this response type, which it will take care of re-serializing and sending back to the appropriate socket to match it up with the right request. So we don't have to deal with any of that stuff, and we don't want to deal with any of that. So what we do wish to do is we're going to get these requests. We kind of want to slot ourselves in right here, but replace this syntax, this unideal syntax. We basically want to get a request and we want to try to match it against our API, just as what's happening here, except without this partial function pattern matching syntax. And if it does match our request, if the API does match the request, we want to parse some information out of that request. Ideally, we want this to be a nice typed API. So we're going to have this some kind of API description that we don't really know the shape of it yet, but it's going to be built with some input parameter. So this API is describing basically pulling this out of the request, pulling this input that we're going to get from the request out. And then we're going to run some function with that input, which is going to generate some output type, which we kind of want to serialize back into our response. So what our API needs to do is not the full request response cycle, but it's more, we want to do a couple of things. We want to parse information out of our request. So we kind of have this request parsing component, request parsing, parser, which is going to basically go from request to option of A. So we're going to try to get some information out of this, and maybe I'll say input here. So we're going to try to parse this input out of the request. So to go up above, if this was that UUID, this kind of is our input field, we want to try to parse this UUID out of the path, users/UUID, and pull that UUID out. But then we want to be able to get that UUID if it exists, and then call some function on it, which will generate potentially a ZIO effect that will return some output. And then with that output, we basically want to, maybe a good default would just be to, for now, serialize it to JSON and wrap it up in a response. So we can sort of get a little better idea of what we actually need to implement. And I think to start with, let's just zoom in on precisely the request parser. We could start with that. It's a good place to start. Sometimes, you know, designing these APIs, there's a lot to do. There's so much to do, and it can be a little overwhelming. So just picking something out that you know needs to get accomplished, some orthogonal component of the overall design, and just get started with that. It's also sometimes okay to just stub out things with types. That would also work. But to actually get to some real coding, let's not just stub this out, but actually explore implementing this request parser piece. So this is our semantics. This is a piece of our semantics. And so that means we want to build some form of syntax, some essentially declarative DSL, a sealed trait with case classes, that we're going to be able to write a function called interpret and get back our semantics. And our semantics in this case happens to be another function from request to option of input. And so our syntax is parameterized and our semantics are going to be parameterized here. So that's basically the first goal. So let's start doing that. Let me steal this little thing and make a new file called API. Okay. Oh, I don't know what that. Oh, that was my UUID from before. Okay. So we want this to be a sealed trait. Great. And it's going to have at least one type parameter. We know it's going to have an input type, and eventually it's going to have maybe an output type as well, but we'll add that later on. And in fact, this API might not need to be a sealed trait. Let's actually break it down a little bit more, because we were talking about orthogonality and saying that this request parser is a piece of our API, maybe not the entire thing. Our API also needs to match different methods, potentially like post and whatnot. And that is kind of a separate concern from, in this case, matching and extracting information from the path that we've been provided. So we can actually kind of separate this a little bit. So I'm actually going to call this path. So this is going to be a sort of a path parser. And our API, and so far it has an input type, will basically be able to just contain, for now, a path parser. And it might also contain a method, right? Some sort of HTTP method. Maybe we could just steal that right from ZIO HTTP. Whoa. There we go. Okay. So our API could be this case class that basically is which method should match this API, and then which path should match this API. And we could actually, even just to sort of give an idea, like let's make one stub here, which is let's interpret a request. So this is our sort of our parsing a request function. And we're going to get back an option of the input. So we could say if request.method equals method, yeah, we'll do it something like this. And if it does not match, comparing unrelated types, is that not the same type? Method, HTTP method. Huh. Let's just do method there. Okay, seal check, good, good. Now that it's the right type, I don't know what I've imported instead. Great, so if the method matches, then we also want to basically make sure that we kind of want to delegate to this parse method on our path type, which we can create, parse, and this is going to be this this thing. Okay, so this is going to get us back an option of A, and we'll leave this abstract for now. So here's just a little stub for us that represents our interpretation. This whole method is essentially an interpretation of our API. So it's going to basically make sure that the method matches as well as the path, which is going to be defined by its own interpretation, which is this parse method. And a path is this special type, but we're actually going to here, maybe we could just make this a call segments. We can make this a list of string that represent the different segments of our path. And I think there's a toList method on the path that will turn it into this list of segments. For now, I'm going to leave this unimplemented. And we can just start by thinking about the different cases of matching our path. So now we're zoomed into this problem of nearly matching paths. So let's get some examples. Let's get some terms that we actually want to think about parsing. That's always a good thing to do when you're designing an API. What are concrete terms that we can think in and use to sort of flush out edge cases and just the basic functionality? Maybe even think about future functionality so we don't design ourselves into a corner, whilst staying as simple as we can in our implementation. So paths are things that look like this. We have users and then some kind of ID, and thanks to Copilot for fleshing out some, okay, it's just going to keep nesting there. But yeah, we could have users, we could have users home, and then we can have these different types. Maybe this is a UUID, maybe this is a string or something. So this friend ID and this ID, these would represent things that we'd want to parse out potentially, different types. So like a UUID maybe, or an int, or a string. So far, what I see three different terms, at least, that we'll need to get started here. And often when building these DSLs, we have sort of our leaf nodes, our base cases, leaf nodes, base cases, different terminology, base cases, and then we have our branches, or these inductive recursive cases, So another way of thinking about this is you have your constructors, and then you have your combinators. So lots of different words. I'm just going to use all the words I can think of, just because maybe we've referred to them by different things, but it's all the same sort of underlying idea, which is that you have some terms that can exist by themselves. So just, for instance, just matching users off a path. If your path is just users, that could be its own thing. But you can also just match a UUID or just an int without anything else. These are sort of two cases. Maybe I will call this one the literal case, because we're matching things, literal strings like users or home or friends. And there's this other case, which is kind of this, I don't know, maybe I'll call it extractor. It's hard to name things. So this is going to basically match out these different types for us, like int, UUID, string, etc. So we're gonna match on certain things and parse them. And then there is the combination case. So this is the combinator, where we have maybe a literal and then extractor component, and we kind of wish to combine them. In this way, we sort of want to combine them sequentially, going from left to right. So I'm going to call this, for lack of a better term, a zip thing. So this is going to allow us to basically take a path on the left and another path on the right and get back a new path. So let's actually now that we've explored this in comments, see what this actually looks like in code. So we have our seal trait path. We have these different explorations of terms. Let's see if we can build an actual data type that represents these different patterns. So one thing we'll need is a literal. So literal just contains a string. Of course, because this extends path and path as a parameter, we'll need a type in here. And Copilot, I think, is probably just going to recommend unit, which is what we'll go for here. Just because there's no real information that this literal string can provide us that we don't already have. We already know we're parsing this string, so it's either going to match it or not. There's no special value of any particular type that we care about here. And the next one will sort of be our extractor case. And this one does need to pull out different types depending on what you want to extract. So this is going to extend a path of A. And how can we? Well, looks like a Copilot has a suggestion, but we can basically take the string and attempt to extract a value. So we'll just try to pull out an int if it's like users 1, 2, 3, but it could have been users hello, and then it should fail and not match. And there are a couple of maybe semantic concerns here that can work differently. For instance, if we have multiple APIs, do we want, if we have, say, 2 paths, one that tries to match an int and one that tries to match a string, is that something that even makes sense? Should this fail and then fall back to the second one, or should this blow up entirely? I think for now I'll have it fall back, but you'll notice at different points in your API design, and when you start to implement the actual interpretation of these, when you start to actually define the semantics via implementing basically these interpreters, that what you've done will actually define a set of semantics. And you want to hopefully have a clear idea of what those are and what the trade-offs are. In reality, the semantics of many things is just defined by their actual implementations. And it's hard to maybe reason about except to say that's how it is. Like the Scala compiler, for instance, it has pretty all right semantics most of the time, but a lot of it is just like, well, it's implementation details. So you just kind of have to keep trying things until it works the way you want it to. So I will consciously note that it's just for now going to fall back if it fails to parse, instead of throwing some sort of other error and failing the server. It could still match a later route if this parser fails. And then finally, we needed this connector case. So I'm going to call this zip, give it 2 type parameters, because basically we're going to have a left path and a right path, and we're going to get back a path of a tuple for now. Okay. And with this, we kind of have the ability to represent these things if we wanted to, these ideas. We're not quite sure that we can actually implement this parse function yet, necessarily, but it feels like to me that we can represent at least these strings. Maybe for this, we want to give it like a name as well, so we can sort of print out. Oh, I have a hand. I saw a hand notification. Yes, I don't know how to. How do we do that? Is there a way to like? Oh, it disappeared. Is there still a hand up? Raise your hand again.
There's someone who says you're writing. We have one question. Why do you use unit and not nothing for literals?
So if we have nothing here, let's think about that, because it's not sometimes that feels right. The problem is, if we look at what we eventually want to do, we eventually want to take whatever that A type is and return it. And nothing has no values. Nothing is an uninhabited type. So we can never, this would basically have to always return none. But we do want to return some in the case of literal, because the sum represents the fact that we parse this successfully. So if it's literal users, we want this to, if given users, return a sum of something. And if the type were nothing, we couldn't actually provide any value here. So we couldn't ever do sum. But there's no real useful information, but we need to return something. So unit, the next arity up in the chain, so nothing has an arity of 0. There are, a cardinality of 0. It has no types. The next one up would be 1, and that is unit. So unit is for specifying just sort of the smoldering remains of an idea, but there's nothing actually valid or valuable there. So that's why unit for now. But it is going to give us some difficulties, as we'll see in a moment as well. Okay, let's try to construct a couple of these. So path examples extends app maybe. So let's copy some of these guys and see if it can be clever for us. So all right, users home. All right, hey, look at that. So they wanted to do something that doesn't exist, but I actually do want some piece of syntax here, and I want this. So I'm going to create this syntax, which unfortunately it's being extra clever and defining it on literal because it knows that this is a literal. So I'm going to do one last step, which is it can often be nice to have these things be private or package private, and then expose some higher level types here. So I'm going to say a value string. This should return a path of units. And this is basically just going to delegate to literal. But I am here widening the type to path of units, forgetting the fact that this is actually the literal type. We can widen it by making these constructors. You cannot widen automatically if you use the literal constructors. That's kind of why it's nice to re-export constructors that are more limited. It also allows you to change the internal implementation later on. So you generally don't want to export or make public your case classes. And now that we've done this, if I have IntelliJ be clever and create a method slash, it's going to do it on the path. So I will say that, give it a type of B, path B, and then I will say path.zip, self that, self fix the spelling, and widen once again, this being path of A, B. Tuple of A and B, rather. Cool. So now we get the syntax, which is kind of nice. And there's one last syntactic improvement we could possibly make, which is to make this method actually an implicit conversion. So we can just do this rather. Cool. So we have users home as a value here. And if we wanted to, we can maybe make a render method. So we're not quite looking at our actual intended final interpretation, but this is actually another valid interpretation with its own semantics, which is rendering it to a string. So let's see if this works. So path literal, there is no empty path. Segment, which is just a string. Case, it's being a little clever. Sometimes, by the way, it can be nice to define. I found this. If I've been changing my sort of development to work nicely with GitHub Copilot. So Copilot, if anyone's using it, looks from the line that you're editing on to the top of the file. It does not look down. It only looks above you, which can have some drawbacks because since the sealed trait was previously above the object, which is usually how I organize my files, it has no idea about the constructors unless there were sort of other methods above it which revealed the structure. So by inverting it, now if I type something like self-match, it should be able to, I'd imagine, figure out everything correctly, which is, yeah, pro tip there. Okay, and because this isn't really renderable in some nice way, I am going to give extractor a little name so we can make this a little nicer. So I'll actually say name, and we'll just do name.toString. Cool. And then, yeah, I think that's what I want to do for the rest of this. I don't think I want all those slashes around it either. There we go. So let's see what users home becomes when I say users home dot render print line. Path literal required path of A. This is always a little fun self match. Oh, really? I'm surprised it's so angry at me. Self dot as instance of path. I don't care. Will that help you? Just want it to work as quickly as possible. Okay, that'll help it. There are other ways around this, but to help the pattern matching not annoy me right now, I'm gonna do that. Okay. So now we see users home down here, and I'm going to up my console font. Console font. up to way bigger. Size 2? No way it's size 2. Cons. Is it really set? What's going on? Okay. Whoa, 24. There we go. All right. Hopefully that is now nice and big. Yeah. Oh, yeah, better. Okay, it's a little bigger for everyone. 28. Huge. Nice. All right. Okay, and let's try with these other ones. Path extractor. Okay, there is no extractor method. Let's make that really quickly. Implicit def extractor. Def extractor. And if I put it down here, once again, it should be a little cleverer about figuring everything out. There we go. So now I can put it back at the top. But yeah, Copilot kind of makes you want to reorganize your files a little bit by having the literals maybe at the top so everything else can use them. Okay, so down here, yeah, we have extractor UUID. And then this doesn't quite work to go from a string to an option. So I need to, let's pull this down. I kind of want to do scala.util.try UUID from string to option, which is very verbose and horrible, but it does work. And in fact, this is why I want to extract this extractor into a constant that I can put on the companion object of path. So we can have some literals for like int to int option. No, I don't need to try there. It's a little too literal. In fact, I could just do to int option and so on and so forth. String to int option. This could just be sum and so on and so forth. Maybe we can come up with some other extractors later on, but that's fine for now. So now I can do path.uuid. Okay, and let's quickly print this. Nope, print. And there's users UUID, and let's try this one more time with this most complicated case, users UUID friend string, and print that out. And so yeah, users UUID friend string. So if our semantics of this DSL is to render it as strings, then we have succeeded. Though the interesting thing about having declarative DSLs and having this single syntax is that you can interpret it in multiple ways. This is one of the things I was trying to get at in the free structures and church encoding lessons, which is that by having a declarative syntax, you can interpret it into semantics A, semantics B, semantics C, all these different ways. So finding some representation, though, a single representation that allows for these multiple interpretations might need to sort of complicate it a little bit. Because semantics B might need some information that semantics A does not. And if you wish for a single DSL to support all of these, it sort of needs to contain a superset of all of the information to interpret everything else. But so far, if our semantics is merely printing string representations of paths, which could be useful in documentation generation, then we have enough information. But let's actually get to the semantics that we want, or that we started with wanting, which is the parsing. So let's see what we can do. So what I actually want to do here, you can implement it directly here, but there are going to be a couple problems with it. One is that, as we saw before, IntelliJ might get angry with us as we try to match on this. Or it just might give us false negatives. Sometimes I like to implement these. Another option, instead of matching here, is to implement it on the cases themselves. So if I delete the default implementation, these things will now turn red because they're missing implementations for the abstract method. So let's implement the method here. So each case is going to have to define what it means to parse itself. Okay, so how do we parse a literal, so like users, out of a path? And we can take some of our concrete cases. So we might have /users, we might have /123, okay? And as we know, this path is going to get broken up for us ahead of time into sort of a list of strings. So this is going to be list 1, 2, 3, maybe list, posts 1, 2, 3, etc. This might be list users, something else, home. Now, the first thing to realize is that we have a list of segments, and we don't really care about anything but the first bit. That's sort of Zip's responsibility, is to care about the rest of the path. So we only care about the head of this list, and it can't be empty. So thinking about some more cases that might occur, here are some different inputs. And this is just something I like to do sometimes when implementing a method, is just think of the different sort of scenarios, combinations we can get ourselves into. So there's a special case of an empty list. There's this, and then two cases where the head of the list matches our string or it does not. So in the case that it matches the head of a non-empty list, we're good. And we want to return a sum of unit. In any other case, we want to fail, which we're doing with the none in this case. So let's see. Okay, Copilot's pretty good here. So we're getting head option and making sure that it contains our string. That is a totally valid thing to do. And we could even make it sillier by saying option.when, which basically does the same thing. I won't do that, but that's a fun method sometimes. Okay, so there we go. That is parsing literal. Let's keep going for extractor. For extractor. Okay, and it's almost the same thing. If I pull these things down, it's almost the same thing, except let's imagine we have 1, 2, 3 and hello, and we have an extractor of, let's say, int. So, well, if it's empty, we want to fail. If it doesn't successfully extract the int, we want it to fail. So it's really almost identical, except we want to call, like I can kind of copy this. I don't want Copilot to do everything for me. So we want to make sure there's a head, but instead of containing string, we want to sort of flat map on this option and call our from method on it. And then we get an option of A. And we can just return this. So that's kind of nice. Yeah, and that's that. I suppose we could have also just mapped to unit here, but yeah, so I think that'll work for this one. And then for Zip, maybe a more complicated one. Let's see what we can do. Let's let Copilot do it for us. Yay! And Copilot really tried its best here. In fact, it type checks, which is wonderful. However, type checking is not always the end of the world. You know, if it compiles, it works. That is not always true. That doesn't mean you should dismiss that as a useful tool. It's still tremendously useful. It's just sometimes there can be different semantics that technically type check, but not all semantics are equal. It's not the semantics you want. So what are the semantics of this implementation of parse? Well, if we look carefully, we'll see that we are parsing the entire list of strings with each parser. And if we think about a simple example of let's say users / int, and maybe our path is list of users 1, 2, 3, we're basically we're splitting on the left is going to be the users literal parser. This is going to be the int extractor. And we're passing to both the users literal and the int extractor the entire list of segments, which will parse out successfully in the case of the users literal, but the int extractor will also get this same list. And if we look at it right here, we're going to see that it's going to get the head option, which will be users in this case, and fail to parse it into an int and then blow up. So what we want is the parser on the left to actually consume some of this list. And there are multiple ways of thinking about this. And to go back to that sort of functional way of thinking, that A to B way of thinking that we discussed earlier, what do we need to know? What's sort of the knowledge? What's the information that we require? What would be most useful to us? Said directly, not worrying about any sort of how we're going to get it just yet. And really, when we parse the right-hand side, we need to know what are the remaining pieces. We want to get a list of string that represents the remaining components, the remaining segments. And so there are actually multiple ways of getting this information, which is why sometimes it's useful to propose these quandaries as in the form of a sort of a type signature, an arrow like this. Because sometimes there are multiple ways. For instance, we could get the number of some n here, which represents how many pieces did the left-hand side remove. And with that, we could take segments and then sort of drop from that n. So that's kind of one valid way of getting that. And often there are many. Clearly, maybe one of the most straightforward is always that identity function, which is like, okay, if we just had the list of remaining segments, then we could just, well, then we have them, right? That's easy. And in fact, that ends up being probably the most straightforward to implement here. So we'll just do this directly. But the point I want to make is that sometimes there are actually multiple ways of deriving the information that you want. And that's kind of the beauty of functional programming, is that you can think in terms of what you want and then sort of work backwards to figure out how you're going to get that information. And each of these different options has different consequences in terms of performance, in terms of ease of implementation, and you can balance that out depending on your circumstances. So maybe, yeah, a strange tangent, but something I try to think about a lot. Okay, so what we've learned in this is that we want more information than we have. And it's really not possible, given the current signature for parse, to get that information, which is totally fine. Like, we did not dig ourselves into a huge hole. It's really easy when writing parsers, if you haven't done it a lot of the time, to get yourself into this bind. It's not always immediately obvious, but there is this, if we think really clearly about the semantics of what we're doing here, we're parsing left to right. And maybe that was implicit in our thought process. We didn't think about it. And as we know as programmers, is that anything that is not clearly specified in our brains is not going to make it into the program. And these bits of implicit knowledge, when unrealized, are sort of latent. They're bugs that are waiting to happen, unless you get lucky. And then you might break it later because you didn't quite understand why it even worked in the first place. So there is this sort of left to rightness of our parsing. And so, yeah, now we are going to take care of that by sort of increasing the scope of our parse method a little bit. So I'm going to jump up to the original definition, path.parse, and change it. So instead of just an option of an A that's not quite good enough, we actually want an option of the remaining segments and an A, so that we can use that, and that really in our internal implementations of these methods. What's interesting, though, is that what was consuming this previously, up above here, doesn't care at all about the remaining segments. That is really an internal implementation detail. It's some information we need to make sure that these different path parsers work correctly, but consumers of this API don't care at all. And this is where you might want to have some sort of internal implementation that does the more complicated thing, and just sort of delegate to that above. And we can map out just the bit that we cared about, so that the consumer up here is happy, and our abstract method can do the more complicated thing. So you don't have to rewrite your whole application just because you need to change your API. Just make a higher level method, write that in terms of the lower level one, and discard or translate between the two levels. Okay, but now everything else is broken. So let's quickly fix that. I'm going to, what's the easiest way of getting this new signature? Okay, I'll just say parse simple, parse simple, parse simple, and then list of string units. And is that enough? Can I do that here? Okay, yeah, it's not correct, but I just want to do as fast as possible. Great. This is going to be AB in this case. Are you happy there? Almost. One more tuple. And then here, this needs to be A. Okay, and everything also is broken because we're now returning the wrong things because we need more information. Luckily, let's just go through from the beginning again. For the literal case, the literal is only ever in charge of parsing off a single element of our list, a single segment of the path. So in the case that it does match, we can just return segments.tail as the start there. Same with here, we can map, and if this did work, we will just add segments.tail to the front. And now in this, we have the information that we need. So we have remaining, and we can use these different remainings here. Okay, why is that sad? Let's do that. Doesn't know what that is. Why don't you know what that is? Import Scala predef. All right, I'll do that. Oh, I guess I'm screwing something up. Option any. What is remaining? Any. Oh, because I'm not calling parse simple. I need to call parse impl. So that's a good thing to do. Great. And I guess now this other syntax will work. Okay, cool. Okay, and now with all that, we can actually try to test our little path parser here. So we have a few of them. So let's try to example path, list of users 1, 2, 3, friends, hello. And then let's see if what we parse from this information. And let's actually see the type of this. It's actually going to be quite ugly because it's basically all these units that we introduced are just getting tupled up at every time. We're not doing anything to deal with it. So we get this kind of awkward nesting. And we're going to take a look at how to deal with that. But let's just see what we get. Theoretically, we should get back an option of A. So we should get back an option of this type. So I would expect to see an option with, in this case, let me make this an int and regenerate this. Great. So I should expect to see 1, 2, 3 in the string hello in what we get from this. And I do. And it's really disgustingly nested here, but we do get the information that we required. So our path parser is mostly working. Let's check this against something. Let me just make this not a string, or I can change it in multiple ways. Let me make it minus friends. This should fail. That fails. Yeah, if this is not an integer, this should fail as well. Yeah, none. So it has to be an integer. It has to match everything correctly, and so on and so forth. One could think about other situations. For instance, what if we have some dangling stuff? Well, I think this will pass because we in no way at any point made sure that there is no dangling bits of information. Maybe that's good, maybe that's bad. We could fix this if we don't like that. But the semantics are basically what is to the right of your equal sign. How do you actually run these things? How do you interpret them at the end of the day? And hopefully that sort of is elegant and you understand most of the details of it. But inevitably in complicated things, there's just some arbitrary semantics that just kind of happen the way they do because of implementation details and accidents. Okay, before I go on, are there any questions with what we've done so far?
I think people are pretty good.
Okay. Yeah, I mean, so basically what we've done is implement a parser. Parsers are very common. They show up in a lot of places, and they're not always just parsers of strings. Generally, the shape of a parser is that of some input to like option output, and often with that sort of remaining side in terms of the implementation, because parsers often operate left to right, at least in the Western world. So yeah, in this case, our input is a request or maybe a list of strings, and we want to parse out some output that was defined in the type of our path here. Okay, so let's very quickly deal with this ugliness. Since we're designing an API, let's try to make it nice and shiny. This nested bit of units and stuff is really quite horrible. Luckily, in the past, we have talked about path-dependent types and sort of type-level functions. And there is a tool exported by ZIO that we can use in this case called Zippable. And what this is, it is this path-dependent, it's like a dependently typed function, which can essentially take a look at the A and the B during the zip case and decide a new type for us, and also implement the zipping of A and B in different ways depending on what these types are. So if we have units and some non-unit type, we're going to get back, so some non-unit B, we're going to get back B. If we have 2 units, we're going to get back units. If we have A and B, we're going to get back a tuple of A and B. If we have a tuple of A, B, and C, we're going to get back a threeple of A, B, C. So it's this sort of function that can do all of this for us. But the very cool thing about dependently typed functions, where that the output type depends on the input types, is that the Scala compiler actually knows at compile time what the type of the output is. And you get that in your type signatures, and you can generate those types, and you get autocomplete based around those types, which is a very powerful and wonderful feature. Let's see how to actually do that, though. So the first thing we need to do is change zip slightly. I'm going to rename this to zip width, and I'm going to give it a third, if I can, rename it to zip width, enter, please. Cool. So I'm going to give it a third argument and a third type parameter. So the third type parameter is going to basically be the output type. And I'm going to give it this combine function, I'll just call it f, which will take the A and the B and return a C. And it will now be a path of said C. And the implementation will have to change very slightly, but it's quite straightforward, where now we just have to call this f function on the A and the B that we get to combine it. So instead of just tupling A and B up, we get to customize how we're going to combine those two types. So one can imagine if we wanted to a default zip, we would just pass in the tupling function here and regain our old zip behavior. But we want to use instead the fancy dependently typed zip. So to do this, we need to have an implicit parameter here, implicit zippable AB. So it's going to basically synthesize a different zipping function depending on the types of A and B for us, whose output type is going to depend and be known at compile time. And then I can say AB. Actually, I think I need to do, I just need to parameterize this with AB. And then zippable.out is actually that third type that it sort of depends on. Clearly, it's a path dependent type that depends on which zippable was magically synthesized for us here. And then we could say zippable.zip. And I think hopefully this will work. And this will now be a path, not of a tuple of A and B, but depending on the type of zippable that was chosen. So we have a video on this stuff for both path dependent types and type level functions in case that is very confusing. But luckily that's all we need to change. And now if I come down here, we'll even see already that, oh no, this thinks it's a path of int string instead of this horrible type. And so be it is. And if we run this again, we're going to lose that horrible, oh, wait. Oh yeah, have to match on the additional value there. Cool. And now we just get a sum of 1, 2, 3, hello. And if I add one more bit here, like path dot another int, and I add another number here, this is now going to be a threeple. So no more nested tuples. So very useful when you have these sorts of zip operators in your DSLs, which happens a lot in practice, and it's pretty convenient. Okay, cool. So now our API is a little nicer. And we've described at least the beginnings of a DSL for parsing paths. So now let's take a step back and see if we can describe other things in our API. So let me make a companion object to this and see if we can do some of the stuff that we specified in the initial file, which was this. So can we create something like this? Ignoring the output type for now. Put that over there. Okay, so we want it a def. Okay, hey, not quite. Okay, so let's say get. Great. So now we have an API that's parameterized by the path that we pass in, which we already know should be of the right type. And it's going to get us back an API of that type. And we can do the same thing with post. Okay. And other methods as well. I'm just going to keep it to post and get for now. And basically just plopping different methods in here. Great. And so now we can try to test this out, I suppose, if we wanted to. How easy is it to make an HTTP request? Request.apply, what have we got here? A version, okay. Method equals method.get, path equals, is there path? Let me see. URL, can I construct, okay, URL path, and I could probably do a path.from string or something. Path.list, okay, yeah. So, sorry, excuse me 1 second. All right, so we're gonna say method URL. URL. Okay, path equals, and then example path, I could plop that in there. With that constructor, I believe. Oh, because it's ZIO.http, I should probably have called this something else. ZHTTP.http. You happy? Good. Okay. So now we have an example request And we basically want to make sure that our API.get of, let's say, users slash that, oh no, users slash path.int slash friends slash path.string. Let's just start with this. And that's not quite happy because of, do I need to import path.underscore to get that implicit conversion? Okay, I think I need to import the implicit conversion and then it will fire on the first parameter. So if we wanted to, we could put that in a package object or something to make that less awkward. And I guess at this point, I can just do this stuff if I wanted to. Okay, so now here is a get users friends API thing. And now I can see, does this parse this request? And it does. Let me comment out or delete all the other prints so we can see that, yeah, it totally is printing out this one down here. And if I change this to 555 and this to Adam, we'll make sure that that parses it out correctly. Yeah, 555 Adam, cool. And if I change this to API.post, it will not match. No. Or if I go up here and change this method to any other method, it's not going to match anymore. So we have this sort of orthogonal parsing that's going on where we're able to match both the method as well as a path. And we get this, we sort of built this pretty nice, if I may say so, myself and constrained sort of correct by construction DSL, because everything would basically be private except for what we expose here. So it really wouldn't be possible to define a path that doesn't make sense or an API that doesn't make sense. Okay. And so this is a very big component in our server. It's not everything yet, but let's at least take a look at how we might use it inside of our backend. So in this case, what was ID? We wanted to parse a UUID from this. Okay, so we want to parse a request. So let's instead use our little API thing. So I'm going to say get user, and I'll say API.get users, UUID essentially, import path. Oh, and I'm going to do objects, APIs, just to isolate this stuff, and import, what was it? API.path. There we go. Okay, great. So now that's mostly happy. Okay, so what we could do is have this matcher. I could say get user. I could say parse, which is a function now. If we look at this, it's a function from request to option of UUID. And I can use this fancy method called, I think, does that not work? Parse unlift. Okay, there we go. There's this fancy method unlift that will turn a function from A to option B into a partial function. And the cool thing about this is that we can actually use this instead. And I can say API.matcher, APIs.matcher, and I can pluck out the UUID here. So I can basically remove this, and I don't need to do that unsafe parsing anymore because it's going to be taken care of as part of this function right here. And let me actually make some kind of little log message here. So yeah, let's just do this for now. Request.method, request.url. Okay, so now if I go back to, if everything recompiled, which seems to have, yeah, okay. I'm going to go to my users page, which there are none. I'm going to create myself again. Then I'm going to steal my UUID and go to my own page, and it seems to have worked. And now if I go here, we'll see that, yeah, it called API parse get, and it parsed essentially the route we wanted. So clearly, this is not how one would use the API exactly, by creating a partial function out of the parse method and sort of awkwardly replacing it in the pattern match. Like the whole point is to not use this pattern match syntax. But this is basically could be used as an implementation detail in our final implementation. But we would need some more information so far because we don't have everything to create a server. Because only half of it is pulling information out of the request. The other half is generating the right response and actually doing some logic. So while we've handled half of the problem, which is pulling information, typed information from a DSL and interpreting into this basically request parser that can peel off the corresponding whatever typed information from it. But then we need to deal with this bit, which is how are we going to take that information and turn it into a result, into something that we can serialize. And there are a couple of things to think about. One is that maybe this concern is kind of separate from our API. If we were going back to up here where we had this trait, this is kind of what we want. This is the analog in Scala to what we want our API DSL to do. It's to describe an interface. But we don't really want an implementation here. That would make things a little awkward, especially if we think to other semantics for our server. For instance, one might be a client. We could take this trait and we could, from this trait, create a client out of it, potentially. One where instead of matching on the inputs and returning the implementation, you get to call this API and it will make fetch requests, maybe from Scala.js, to your server, which will have been implemented using the same API DSL. So you don't really want actually to add handlers to this particular API DSL. This describes merely the interface. So we might want to imagine, let's use a little functional chain here again. So we have an API type, which is great. So we have our API. We eventually want a server, which in order to have a server, we kind of need a handler. We need something that can take our A and return a response. And so maybe instead of just going from API to server, which would mean that that handler needed to exist in our API type, we could instead sort of have a function or maybe a data type where we sort of have this handler type that contains an API of A, but also the handler function, which goes from, if I can type, A to some kind of output. And then basically this handler can be, typed with A or input outputs. If we had our API have an output type on it, then we can make sure that we've sort of created a function that matches correctly. And this we can create a server from. And maybe we could just sort of think about how that would occur right now, which is just by stubbing stuff out. Not sure if we're going to quite have time to do this, but let's just stub stuff out. So I'll say input outputs, API, input outputs. Now the first thing, of course, is that this does not quite have an output type yet, but I'll just make it for now. I'll just lie, and I'll have these all start out as unit. Great. So then we need a function which basically goes from this input to, we could have it be a ZIO of outputs. A ZIO of, for now, I could do any nothing output, or I can add some R and E parameters, obviously, and give them all the right types or whatever. And so if we had this handle function, could we create a little application from this? So let's think about, basically, this is our semantics, again, is a handler, and we want to, sorry, this is sort of our input, and our output is going to be the server. So can we go from this handler to an HTTP app? So I'll say to HTTP, and basically we want to go and get an HTTP that's going to have the same the environment required by our logic, the error from our logic, and then go from request to response. We want this to be an HTTP app, which I guess has its own type. So I could just say HTTP app. which is an alias for that request response. Okay. And basically I can kind of copy what I've done here a little bit. Except in this case, let me separate this. We don't know about the logic at all. And we don't want to use this matcher, but we want to use a matcher that has been defined from our API parse on lift. And so I could say matcher. And this would basically be the inputs. And then I can call the handle method with the inputs, which is great. But now I have an output and I want to return a response. So what can I do here? Well, I can get my outputs and I can say response.text and do output.toString. Yay. So that's clearly not ideal. We don't just want to stringify our output. So, but this is sort of a good case to just drive an idea forward, because now we realize what we're missing in the final implementation, which is we kind of want a way to serialize this to JSON rather. And so we kind of want to call to JSON. And if we write this code, we'll see that, well, we're missing a JSON encoder for our output. And there are a bunch of ways we can do this. One is that in our API, we can put it here. We can say that, oh, well, we need an output encoder. So output encoder. So I could say a JSON encoder, or I'll just make it a codec to just be extra flexible for our output. So we need that. And here we would need sort of a JSON codec for unit. I'm not sure if there is a JSON codec for unit. Is there one? We might have to make one. Yeah, so we can make one. JSON codec, unit, JSON codec. JSON codec. Oh. Let me see what, yes, this needs an encoder. Is it an apply method? Yeah, so I need to make a new JSON encoder. Okay, new JSON encoder. Okay. Is there an empty? No. New JSON encoder for a unit. Okay, let's implement this really quickly. Unsafe encode. Okay, I'm basically going to do nothing to encode this. And for the new JSON decoder unit, it's basically going to be like this no-op encoder. I'm just going to return, behold, a unit. It will always succeed and always fail. There we go. Yay. So now we have our unit JSON codec. And I will replace both of these with unit JSON codec and make that lazy val so I can keep it at the bottom. Okay, great. So that's kind of our default JSON codec. That's obviously mostly terrible. The next thing would be to reconstitute that function we talked about before, which is output. Except with this, I want to basically have a codec. So a JSON codec for whatever output type we have. This is going to get us, I guess, a new output. So I should say output two. And we'll just use that codec there. We're basically copying ourselves. Copy outputs codec equals codec. Oh, output encoder. Output codec. There we go. So now we have the ability to actually do something where I can say val output codec, JSON codec output equals API output codec, and I can make this implicit. Now I can just call toJSON there. And this is basically a way of creating an HTTP app. So let's see if we can get just this bit into an HTTP app. So we need to make a handler, which is right now we leaves something wanting. I'm going to make a new constructor called make, which is going to have, RE input output. And I'm just going to separate this into two segments so that the handler will be defined. Can I get some help, please? Help me. Help me, Copilot. All right, almost. There we go. Perfect. Okay. So by having it this way is that our API is going to help us write our handler a little more easily, which is going to be nice. And so now I can have my user get API. And I'm going to say get, where is it? User get, no, is it above? Get user. Okay, I'm going to delete all this stuff that I had before. Put this down here. Import API.path._. Path.uid. And this is going to, I'm going to regenerate this because now we added that. Oops. Do I not have, oh, because it's the other one. Object API. It's a little annoying just because I've imported all of, you know what? I have a better idea. Renaming this to route. I don't think route exists. And that would make that slightly nicer. Import routes. Okay. Good. Okay, so now I can regenerate this, and it's an API that describes UUID to unit, but we know that we actually want this to have the output of an option of a user. And let's now regenerate the type again, and it's gonna work, I think. Do we have a codec? Could not find JSON codec for what unit? It does not need one for unit. Did I screw something up here? Oh, output 2. There we go. Okay. So now that we have this, I can say handler.make, pass and get user. And then basically I could say users.get, user ID, need to wrap this. And it's the same logic that we had before. In fact, I don't need to map this at all because we needed to return that. Can I even shrink this more? I'm not sure. No. Okay. So here's our handler. And then I can basically make user app handler.toHTTP. And now I get back an HTTP app. And I think this is saying nothing only because I'm using the accessible macro, which is screwing me up right now. So I'm going to fix this by saying def get ID, unfortunately, ZIO service with ZIO. There we go. And I will have it create the other ones for me. There we go. So thank you, Copilot, for the accessors that will actually give me right types. There we go. So now this is going to have the right type when I regenerate it of users throwable. So it's totally inferred the environment from the function that we used here, and so on and so forth, which is pretty dandy, which is pretty handy. And the nice thing about this is that ZIO HTTP has composable HTTP apps, so you don't need to necessarily handle everything in one of these collects. So down here, I can basically zip together my get user app, or whatever what I called it, app user app, with the other app and run this server. And let's see if this compiles and runs. Okay, I think it's already running. And let's go through the rigmarole once more of, okay, now there's, well, it did work and it returned null, which is the JSON encoding of none. But if I just go back through here, create myself again, copy my new UUID, paste that in here, we get myself. And this time it has actually went through this whole separate path to do that by using the HTTP app that we generated from our API DSL. Now, there are clearly things that remain here that need to be done a little more nicely, perhaps. For instance, it would be neat to have sort of multiple HTTP apps, or make this easier to write. Since we only have 7 minutes, maybe I can show off one thing, like maybe one ideal way to really compete with this stuff for now is to just do something like, okay, now that I've specified this API, maybe I could just say to HTTP here and give it a handler. That would be kind of nice. Is that possible? Let's see. Create method to HTTP. RE F. So this is going to be a function from input to ZIO RE output. And this should get us back an HTTP app of R and E. And basically, I can say handler.make, and import that. And then I can say this, what was it? Handler make this F to HTTP. Yay, okay. So now we can have this even terser version of everything. So I can plop this down here. And that's kind of nice. And it's getting to the point where it's like almost nicer than, oh, sorry, Siri, than this case statement, because we're able to parse out like non-trivial information and just be able to write it like this. I think another step would be to, well, since if we're defining it like this, we don't need to define the output. That's going to sort of be obvious based on what we return here. So we could remove this. And basically, we'd have to turn this into instead an implicit extension method on API. In the case that the output is unit, you get to override it in your own custom way or something like this. For now, to get this to work, I'll just say output 2. And then codec output 2. Copy output codec equals codec. Yay, okay. And now that will work as well, I believe. What's wrong with you? Missing argument list. Oh, I did not make it implicit. Okay. In the actual ZIO API library, these are defined in an extension method so that you can do this nice terse format if you feel like it. Though if the output is anything but the default unit, you will have to change that. So yeah, now we could basically create a bunch of these and then zip them together as individual components. And that can kind of be a nice alternative to the collect ZIO approach. It can be more expressive. You can do a lot of more interesting things that we haven't done, such as adding like header parsers or query parameter parsers. So you want to match a parameter called email of type, int or something like this. That would be possible as well, and it would match this, and that int would be now part of your signature. Likewise, with dealing with sort of JSON input as well. So you want to parse this create user type that we have above that we're using for our post handler. You can do that, and it's going to take care of this really sort of verbose and annoying thing of parsing the body as a string, then using from JSON, and then converting that to a ZIO and whatnot. I mean, you could basically make some syntax extension method on request to do that yourself. But yeah, it can do a lot of things. And then obviously generating corresponding clients would be the other bit from this. But we only have 4 minutes left, so I can't unfortunately do that in time. But I hope this was at least interesting. We got pretty far, further than I actually thought we would, because we were able to implement at least creating a DSL for a somewhat non-trivial. I mean, this could be used in very basic apps that only need to parse paths for get and post requests and no input bodies, and then handle the response using any kind of ZIO libraries you want. So yeah, anyway, that's sort of what I wanted to talk about today. I hope that was interesting. If you want to take a look at the actual implementation, there is a PR open on ZIO HTTP GitHub. Got to have a dash ZIO HTTP. So there's a pull request open for pulling this API DSL into the code base, and you can see the actual implementation, which looks pretty similar, except it's a little more verbose, a little more complicated, because it also has a client interpreter and then open API Swagger docs interpreter for this this thing. But if you see down here somewhere, here is basically where's our path type? Path type. Anyway, path type somewhere in here, and it looks almost identical to what we have with a couple of other. Here it is, path. Even though Tushar recommended calling it route for the reason that we we went over today. But it has those same base cases of the literal parser, and I guess I called it a match instead of an extractor, and zip with, and there's also the ability to map as well in the actual API. And it has a way more low-level implementation for speed, which is one of the other things that you can do with this is really go crazy, because basically the internals are very nicely hidden away, and you can create all sorts of internal mutable states, and it's all hidden from the user because it's all in that interpretation layer. So you can get really wacky and make it as fast as possible. And it ends up being like 8 times faster than the collect method. And I'm not entirely sure exactly how many times faster, but much faster. Anyway, okay, now it's really the end, and I've gone to the end. Are there any questions or anything? And I will post this code to the Zymposium.
There's a question about testing. Is it worth dealing injection and test your handle functions?
Oh, could you say that one more time? Sorry.
There's a question about testing. It's pretty, but is it worth dealing with injection to test your handle functions?
Injection to test your handle functions. I don't think it would be too difficult to test it. I guess it depends how you want to test it. But I think ZIO HTTP has some testing abilities that are built in. You could use it with that. I mean, if you want to basically throw requests at it and make sure that it parses correctly and runs your correct logic, I think that would basically be a matter of using ZIO HTTP's testing framework for that. I don't see any difficulties with testing, but if maybe we could look at that some other time, maybe next time, or whatever. But yeah, just if you could elaborate on that, and maybe I'll check Discord after. I'll try to answer.
Yeah, I'm looking. I don't have any follow up on that one yet.
Cool. Any other questions? We're all good.
No, I don't think so. That was awesome. Thank you.
Thank you, everybody.
Oh, hold on. I think he's typing right now. Maybe if we want to go a second here. Phil, you want to? Let's see. Oh. No. All right. I think we follow up on the Discord.
Okay. Sounds good.
All right. Bye.
Take care, everybody.